and just put Mabel.
I'll figure out. Maybe I can figure out a way.
Just wrap her in her little.
Figure out a way.
Wrap her in her blanket, and just Mabel.
Because if you get to hug her, then like magic dust comes into your
An
brain.
enlightening experience.
Let's close this door so Isaac doesn't come by.
You think he won't? You think a closed
You
door?
probably, yeah. Who
You think a
knows?
closed door is
You
gonna
did
stop
seem to
him?
have no concern whatsoever for decorum.
That's hilarious. Which problem were we talking about? 733?
Yeah. What were we talking about? Let me give you what I'd like you to start on, because we need to finish up this stuff so we can get to the chaos. But this is like right on the cusp of it, so it's literally like a bifurcation point in some ways. So I would like you to please read 8.1 and 8.2, and if you're Kayla, read 8.3. But we should all try. Let's all try to read 8.3. But Kayla's going to be the one who actually probably understands what's happening in 8.3. It's an example of a chemical reaction. Trinity probably also has a better shot than you or I.
Yeah.
I changed majors so I didn't have to finish Gen Chem.
Oh, seriously? Okay.
I mean, there was more reasons to it, but computational physics major doesn't require general chemistry.
Makes sense.
Regular
Makes
physics
sense.
does.
Yeah.
I took Gen Chem 1 and I said, I'm not doing this.
Took UNC Chem in high school.
I wish I knew more chem. That was back in the day when I was like when I was doing math. I was such a hippie that I didn't want to do science because I thought science was arrogant and making I didn't want to be told what the world was.
Yeah.
Fair.
Now I feel different. Now I feel like there's a place for that.
Yeah.
But that was such a
There's a lot of cool stuff that happens in chemistry when you understand it.
yeah, definitely.
It's the understanding part that gets me.
And then probably this assignment we're gonna need to talk about 8.16. There's a couple in here that I think it might be this one.
Oh, 8.1.6, not 8.16.
And I some of this we'll have to definitely, I think a good portion of this we'll talk about together. This stuff here is on a new kind of bifurcation that we've never seen before. So this is about what are called Hopf bifurcations. Hopf.
Ooh, fancy.
Yeah, and that's cool. That's like we've reached the pinnacle of talking about bifurcations in some way when we reach that. These are 2D bifurcations, which I kind of want to start on today. And you already understand enough to understand this section. It's really just like an expansion of the basic kinds we've already seen, right? So transcritical, blah, 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 blah. All that stuff. Just with another dimension kicked in a very nice way. So let's see, so the problem we wanted to talk about today was, boy, I got like 8 pages of work on this.
Oh boy.
Let's see. Yeah. It was 733.
Yeah.
We had x dot equals x minus x cubed, y dot equals x plus y cubed, and we wanted to analyze, I think the thing was show it has a periodic solution.
Yes.
So step 1 would be convert to polar. They don't tell you this, but if you don't, you will not have a good time. You're gonna have a bad time. South Park fans, anybody know what I'm talking about? No, with the skiing? Okay. Well, moving on. So convert it to polar. Remember how to do that? Let's just really quick, just so that when you ever need this in the future, you remember how to do it. So we have, start with the basic arctan, that should be inverse tan. Start with the basics and differentiate with respect to t. So with respect to t, this one goes 2r dot plus 2xx dot plus 2yy dot. And then that can be clearly simplified to eliminate the 2's. And then this dude here becomes really nice. We do the quotient rule on that argument, and then 1 over that argument squared plus 1. And then quotient rule on top is going to give us that's all gonna be over x squared. But notice how the bottom has a beautiful fraction that gets canceled so sweetly. And so this is y dot x minus y x dot over x plus y squared, which turns out to be r squared. So really, really lovely. And then the way to actually do that transformation is to take this equation and this equation and plug them into those formulas. So right here, we have r dot equals this. So I can immediately go to r dot equals x times, and then use the x dot equation, right? So x minus y cubed plus y times, use the y dot formula. This looks like it's gonna be horrible, but it turns out so sweet. And it was after I did this that I knew this was what we needed to do. Right, not bad. So beautiful, beautiful. Then I've got x squared plus y squared. That's going to give me an r squared. And then minus x squared plus y squared. Excuse me, y to the fourth. Not bad. And that's r dot. We can take this a little bit further. This one was a little, I was like, what do we do here? So what I did was I just went to the classic polar conversion formula from polar to rectangular, and then just replaced x and y with that. So we've got r dot equals r squared minus, and then we're going to get, notice how we'll get a big old r to the fourth out in front, and then just a cos to the fourth plus a sine to the fourth. Check it out, Sydney, let me know. Follow that algebra through. What part's confusing you?
Hold on. Could you do?
Cool.
How did you take that r to the fourth out? Can you do that step?
Because this is r to the fourth cos to the fourth, and this is r to the fourth sine of to the fourth. Just taking these to the fourth.
Okay.
Right? So,
Okay.
does that make sense?
Yeah.
And then just factored out the common r to the fourth.
Yeah.
Yeah?
Yeah.
Okay, groovy. And then divide through by r, which is always going to be non-zero, and we get r dot equals r minus r cubed times this thing here, which is kind of interesting. And I started looking for formulas for it, but then I ended up just doing my own kind of breakdown. Let's talk about it in a minute, but let's get this one done. Actually, we don't need any more. Does that make sense? Why we don't need any more to get a trapping region? Do you see why do I not need any more to get a trapping region? So if I just know that formula, why do I not need the theta dot? Which we could easily get. It's not too bad, but why do we not need it?
It only, when we're doing trapping regions, it only relies on like looking at if r dot is less than or greater than 0.
100%, yeah. We're just gonna look for an annulus, in other words, a punctured disk, where r dot is positive on the inside part, on the inside ring, and r dot is negative on the outside ring. And then that way, what formula? Poincaré-Bendixson?
PV.
The PB theorem, we know that things get trapped in here, so we get a limit cycle forming. And then there's a fixed point right here. So that's the basic plan. The key to getting this analysis is you want to take this part right here. Let's just call this like f of theta. So I'm not gonna do it all for you. You might want to look up some formulas. I think there's a nice formula for this that I've never seen before. I ended up seeing one floating about. I went a different route. What I did, let's see, just to tell you what I did, in case you want to go that route, because I gotta leave this fun math for you to do. Let's see, what did I do? that's okay. Here we go. Here's a better one. Oh, yeah, here's the trick. So take this, and you can rewrite this as cos squared theta plus sine squared theta, which we know has a beautiful, this is just one, right? But square it, and then when you square this, you're gonna get cos to the fourth, sine to the fourth, but you will get this plus 2 sine squared cos squared inside there, so subtract it off. You see how nice that could be then? And, oh shit, I guess I'm doing it for you here. Oh well, no big deal. And then there's like some half angle, double angle identities that might be useful here. Sine of 2 theta, cosine of 2 theta, one of those two. And then what you're going to do is get this in terms of an f of theta, and you need to figure out what is the max of f of theta and what is the min of f of theta for all theta. So you'll have to do, we did something like this before. It was kind of, you know, like sine of something is always between, actually let's do this. So that when this function here is at -1, and you should be able to get it there, r dot is at a max, and then r dot is at a minimum when this thing here, this f of theta is equal to 1, because you're subtracting off the r cubed times whatever. So this is going to be where your min occurs and your max occurs here. And you just need to figure out, well, what do you need to do? Shit, yeah, you will use this fact. It won't be enough to just take this right here. Max occurs here. And then what you'll come up with is an r dot, because so what you want is you want to figure out what is the, so how about this, sorry. So find an r such that r dot is positive using this. So do this analysis here first, get a bounds, get theta out of the picture. That's what I'm trying to say. Get theta out of the equation. And then come over here and then find r such that r dot is positive, and that'll give you this inner ring. And then find it where r dot is negative, and that'll give you the outer ring. Sorry, that was a little chunky, but that's the basic idea. Just get freaking theta out of it, and then you just do some calc, figure this all out. There's stuff to do. There's definitely stuff to do. And there's stuff to do today too, because I can move on. And I think we're gonna need to plot some stuff, so I would like to give you, yeah, I know it's fun, plot day is fun. We should plot every day.
I like pictures.
I do too. I like it very much too.
I always have to tell Cybert to draw me pictures in real analysis, which is kind of hard.
Wait, he's not drawing pictures?
Well, sometimes he explains things in Cybert words, and I'm just like, Cybert, no, please, just draw me a number line or something. Maybe some pictures.
Yeah, it's some, yeah, I mean, some of that shit is like impossible to like, and if you draw a picture, you've just lied to everyone.
Just like, but like some of the things he says, it's like, no, that might make sense. Like, but then he like says it in real human words or pictures, and I'm like, why didn't you just say that? Like, why didn't you just say that, Cybert?
The old Cybert, quit
Oh.
Cyberting on me.
Love that guy.
All right, so this one here, you'll have to use A instead of U as we have been. I think I had trouble getting this in because that thing was weird and I had to do it y dot equal to A minus y squared, but maybe you'll have better luck with it. I'll start getting the analysis up here. You just see if you can tell me what is happening as the parameter moves across 0. What's wrong?
My computer decided it wanted to be dead.
Oh, no. You got power now, though?
Oh, heck yeah, man.
Cool, all right, man. I think that's the system that me wanted. See, it's not taken. It's yeah. It's such a chump sometimes.
A chump.
Try put that down here. That's what I had to do. So change it to Y. Yeah. And I'll send everything. I don't know if your parentheses are hit and miss. Okay, cool. It does like
My
parentheses.
alone, okay?
Okay, I thought I back off.
You're funny.
Oh wow. Huh. That's cool.
It's like this.
Where is my Facebook? Can I put it on this one? Does this one like parameters?
Oh, what's that one?
It's another one. I don't know if this one likes parameters though.
You'll have to, Trinity and I both had to switch the variables.
She's trying it different.
Oh, you are doing that, it's not working, well, something's coming, there's a picture of something.
Oh, that's the
Wow.
That's
Ow.
the old, that's
That's
the
from-
old stuff.
My God, that
Yesterday.
picture's cool.
that's from the homework one.
Yeah, use the one from Bluffington. Cause then you can do the parameter.
Oh, wait,
This
no,
one.
what's going on?
That's the one. I usually end up just, I say Google direction field system Bluffington. That's my new route there.
Okay. Excuse you. Why don't you like this? What? This is dumb.
Yeah, I don't know what's up with that thing. Why it's so challenging.
What are this? Pencil color.
What did you see? Did you kind of get a sense of like, or is it too hard to tell with the resolution? And Yeah. so that's your super negative, right? When it's like, yeah, come take a look over this.
So like this is when it's positive and it has some sort of situation.
Yeah, it looks like a saddle down below, right? So yeah, go back to the positive real quick, please. And then add a couple more. You can see the saddle kind of, right? Like the trajectory is going up or down. Yeah, so you've got an unstable manifold that leads right into that sink. Yeah, okay, that's good. And then and that's positive, and as you move backwards, yeah, they just totally disappear. Yeah, exactly. So let's see, what do we got here? So let's I'll catch you up to speed with what I'm doing. So I took the Jacobian, got these fixed points at plus or minus root mu. When mu is positive, then I can take that square root. When mu is 0, we just get 0, 0 is the only fixed point. And then when mu is less than 0, you have like x dot equals -1 minus x squared, and there's no real zeros for that. It's just always negative. So if we're thinking of the flow as from mu goes from negative to positive, we actually see the birth of two equilibria. So let's kind of take a look at the bifurcation diagram here. So let's see. So these are just the stable points here. There's the Jacobian, and I put those in here so we can use these to classify them. But we have this nice thing that we can do anyway. Here's their fixed points. And then this is my parameter mu. And when mu is negative, nothing. The minute mu hits 0, an equilibrium is born. And then it splits into two branches. We've got a negative or a positive branch and a negative branch. When mu is positive, so I don't know why I do this, but it's because I'm lazy and then I have to think it through like 100 times anyway. But I like to carry through the plus or minus and then make the changes. So that's plus or minus there, becomes minus plus there. Adding those together, it's still minus plus, and then when I do the determinant, you multiply by -1, so it flips the sign. So in other words, when I'm at positive root mu, tau is this, which is a negative number, so tau is less than 0, so that's stable. And delta is this dude here. So that's going to have me over in this part of the plane, and I just got to figure out where, right? So we have a positive delta when mu is positive. So we're over here. Let's see, where are we sitting? I guess that's where I was about to go. I was going to compare tau squared with 4 delta, but I think we can do something a little bit more sophisticated, and I think that's what I'd like to do because it leads into what we're talking about today. So this diagram with the tau squared and 4 delta, yield thing like this, and saddles are over here and all that stuff. That's all great, but we can get a little more sophisticated because I can literally read the eigenvalues off of that thing. Does that make sense that I can just read those off of there? Because it's a diagonal matrix. So the eigenvalues, let's say mu is a positive number. The eigenvalues are going to be just these two numbers. We're going to have minus plus 2 root u and -1. So, and now I have to go back and do it all. So when we have, so at positive root mu 0, the evals are going to be -2 root mu and -1. So if I have two negative eigenvalues, what do I have? Oh man, I'm gonna miss hearing you say "oh shit" like that.
Do you hear her all class though?
What's that?
Do you hear her all class though? Because like I said,
Oh, I do.
I sit right next
Oh
to her.
no,
and it's just
I
a-
know. I've heard, I know.
all the time. Yes, Trinity.
I've been here.
Yes, Trinity. Tell me how you really
We've
feel.
been together for a while.
I love that about you, Trinity.
Just like Kayla has that little pickle thing of me, that little pickle recording where I got excited. I want to get just the recording of it. Shit. That's being my ringtone, because that's how I feel when I get it.
Someone
calls
tries to
me.
get to Dr.
Shit.
T.
God damn it. I do say that, I guess. Yeah. So, what is a negative eigenvector? So you've got, let's just think this through because you know this. I've got an eigenvector, I've got an eigenvector, I've got two negative eigenvalues. Stable node. So right here, because we have two negative evals, we've got a stable node. Cool. that stable node is headed towards 0 as mu goes to 0. And it's moving away from 0 as mu moves away from 0. You can see that right here. And then what do I have at negative mu? 0. What's at negative mu 0?
Positive eigenvalue and a negative eigenvalue?
Yeah, yes, ma'am, yeah. So, it's, again, I fucking confused myself again. So I have evals positive root mu to root mu and negative 1. So I've got a positive and a negative. What happens there? Saddle, right? We've got an intake and an outtake manifold. So here we've got a saddle. So that means that when I look at the bifurcation diagram, I didn't have to get too nitty-gritty with it. I've got nothing, and then an equilibrium appears out of, the blue sky.
The blues.
And remember, this is just the saddle node. That was the generic name for this. So it's a saddle node bifurcation. And this branch here, the positive branch, is a stable node. And this is a saddle. I want to talk about this really quick, right after things disappear. So if we're just thinking about maybe moving to the left with the parameter. So we see this, like here's our little movie that we have. These are on the x-axis. So I've got this stable node here. And I've got a saddle just right across the way from it at negative mu 0. So here I've got a saddle. And so since this is a stable node, this is probably the outtake manifold, just shoot straight across into there. That makes perfect sense. And then I think these actually end up being nicely vertical. So that's your intake. There's your other outtake. And we see some behavior like this. And Trinity got a plot of that. Does that seem about right? Yeah. So this is after the things are born. And what you have to imagine is at that instant mu equals 0, an equilibrium appears here. It is a kind of a messed up one because mu will equal 0. And so we have a 0 eigenvalue. So let's just pick a little note here that at mu equals 0, we have a 0 eigenvalue. And what's the other eigenvalue? Negative 1. And negative 1. This corresponds to degeneracy here. So we have a degenerate node at that point. But it's kind of stable because of this negative 1. So remember what those degenerate nodes look like? They were things like that, right? They were semi-spirals and things like that along the way. You have a collapsing of things. So we have a degenerate node at that point, and that degenerate node then splits into a stable thing and a half-stable thing. Stable and half-stable. Barely stable. I guess I shouldn't even be calling saddle half-stable. It's mostly not stable. What though happens if we think of this in reverse? And that's where I was going with this. As we move from here to there, you can think of them as colliding. So we can think of these two nodes as coming together as mu heads to 0 and then colliding and annihilating each other. But something really cool happens after they annihilate each other. There's this phenomenon called ghosting, which is, I'm an expert at ghosting. In fact, I will just ghost the whole party if I can.
That's phenomenal.
So, let me show you what I mean. Moments before the birth of that equilibrium, we get this little channel that is ghosted. So what I mean by that is things get really slow. So let's take a look here. If mu is less than 0, and we'll say in small magnitude, then the phase portrait actually there are no fixed points at all. 0 fixed points. And what we have is something like this. Again, just a flow going like this. And there's this channel that forms right here. Where for a while it takes forever to move through there. So it's like they're stuck, but yeah, and Sydney's looking at it right there. So you can see it, it's this thing right here. If you're moving through here and you get in here, you could spend your whole lifetime just like moving a couple inches. And I just want to show you how to see that more than anything. So in this channel here, we have a ghost.
A ghost.
Yeah, ghost. So it takes forever to get through. Until mu gets sufficiently negative, and then things clear up and we have some normal behavior. But how do we see this? To see, we're gonna look at just the x equation, because really all we're worried about is like how long is it taking to flow left or right? That's our study for just the next moment. So we have dx dt equals mu minus x squared. And I'm going to solve this, and I'm remembering that mu is a negative number here. So I'm going to do separation of variables. Whoa. No. dt. And then I'm going to integrate. I'm going to actually integrate from negative infinity to positive infinity. So think about over here, if I actually did this, just really quick. If I did this, I would just get T1 minus T naught. Right, that's fundamental theorem of calculus, that if I did that, I would just get the length of time it took to do that. So what we're going to do is we're going to take a look at the infinite amount of time. So we're going to take a look at this, and I'm being a little abusive here, but this is equal to the time it takes to travel the entire x-axis. And I'm going to do the same thing over here. So this integral is going to be with respect to x. This integral is going to be with respect to time. But we can, it's actually easy to believe that as t moves from minus infinity to positive infinity, so does x. Look at the flow. X starts out there when t is at negative infinity and ends up over there when t is at positive infinity. So this seems reasonable. So now I can do this. This is just an arctan because that mu is positive. This is actually going to be 1 over square root of mu arctan x over square root of mu. And then we're going to do that. Let's be more abusive with our notation. Even more abusive. And then over here, this is the total time. But that's a nice old finite thing right there. What is the limit of arctan as x goes to infinity? It is a great question. Yeah. Here's look. If you don't remember anything else that I've ever told you, that damn, it just comes in handy so many times. That's an arctan graph.
Oh.
You're like, I still don't know what you're saying. That's arctan. So it's beautiful. So as x goes to infinity, we get pi over 2. As x goes to negative infinity, we get negative pi over 2. And now, like, wait, should that argument be negative inside there?
Once again, wonderful question.
Yeah, let me take a look at mine. Oh, this should be negative inside here because mu is negative. So that's one thing. That's one thing. And I think the rest of this looks okay. like there should be a negative inside, so then I get, well, let's just fucking do it. So when you plug in infinity, you get pi over 2. And then when you plug in negative infinity, you get negative pi over 2. And then you're subtracting it. Wait, that looks like it's going to cancel, doesn't it? It's something, what am I doing wrong here? So I put in positive infinity, I get that. Put in negative infinity, I get negative pi over 2. Oh, and then I subtracted. Okay, yeah, that was it. So there's some kind of sign that's wrong here. We're just gonna go with it. We're just gonna make it positive, but this is minus pi over 2. Negative pi. Something, why do I have, oh.
Okay.
I guess it's because that whole thing is negative, but yeah, fuck it, whatever.
Yeah.
Yeah, exactly. So pi over root negative mu. There we go. Let's just make it positive. Flip side. I think what we computed is probably the time it takes to move backwards or something like that. Or we're moving backwards, and that's why the time is coming out wrong. I guess. I don't care. It doesn't matter. That's the answer we're looking for.
Okay.
It's plus or minus that. That is all that matters. And since it's time, we'll just make it positive. But look at, this is the total time it takes to travel the entire x-axis. What happens to that as mu goes to 0? So total time of travel is equal to pi over root negative mu when mu is less than 0. What is the limit of that as mu goes to 0? So right at that moment here, when mu is super small, what is the value of this? That's what goes into play. We could play like those word find games where I say, give me a noun.
Shoe.
Shoe. Give me an adjective.
Small.
Which is really big shoe.
Big shoe.
Really big
Yeah.
shoe. When mu is super small. So look, you're dividing by a smaller and smaller number with a fixed top, right? That thing blows up. So all I'm saying is that the moment after mu moves to here, in this region, it takes forever. This is super slow travel. And the closer that mu gets to that 0, the slower the travel. And as you actually approach 0 and get closer and closer, you can get that travel time to be as large as you want.
You might not ever get 0.
You might not even.
You're just going slow.
Yeah, hell yeah. So this is where the ghosting appears. And you can see it. The thing that sucks about that is it doesn't have time. I would love it so we could see that happening. That would be kind of cool. Okay, what time is it? All right, 10:15, good. We have so much time. So you get to explore some of that. I'm actually not gonna go through all the major kinds of bifurcations. Let's do it together with the book. Basically, I'm gonna ask you to read the details, and he does not give many.
Oh, rude.
Which is good though, because you got them all. You already understand these basic bifurcation kinds, and he's like, here, it's just a combo of this and that. So if we could turn to 8.1, that would be groovy. And yeah, so we just did at the top of page 242, the saddle node bifurcation. That's like right after the 8-1 header. And what I'd like you to do is move to page, there it is, page 246. I don't know how to tell you where that's at, electronic book friends. It's right before example 813.
Okay.
Right before example 812.
Okay.
Right before, literally right before that. Do you see that? It's got those 3 equations
Yeah.
there. So notice how they are exactly what we've studied with an additional y dot equals negative y added on. So all those are just those basic forms, but we've added on this stable y behavior. Do you see that that is a stable y relationship? Does that make sense to you? Yeah. Because the solution to that is y equals c e to the negative t. Yeah. So you've just got decay all the time. So that's just to make sure that things are decaying. But the main behavior that this is kicking in with those x dot equations. And then he goes through an analysis you might want to check out for your problems. 813, highly recommended. It's great. I want to start on 8.2 today. I want to start talking about Hopf bifurcations. Our final bifurcation. And these things can lead to chaos. So we really are on the periphery of chaos. The periphery of chaos.
I think I get some of the best words from my math professors.
Yeah?
Yeah.
Well, we're the smartest ones here.
Cyber just throws out things sometimes. I'm like, huh? What?
Give me a cyber word.
What did he use the other day? Oh no, you used grok the other day, but it was that same day that he used another word, and I was like, did you guys just say, yeah, this is the word I meant. You opened a dictionary and you said, I'm using this one.
We're just old too.
Oh,
We've just
relatively.
relatively, yeah, we're not the oldest.
You're up there.
Nice. Yeah. Nice.
But you're cool, old Dr. T.
Thanks. As long as I'm young inside a young spirit.
Oh God, yeah. Oh God, yeah.
It's like so often I'll meet students and I'll be like, you are so much more together than I am. It's like, wow, teach me. You can be my manager.
Please. I'll pay.
I need a manager. So a Hopf bifurcation is when we have like a physical system. You can put the little title up here so Kayla knows what I'm saying. We have a physical system that has oscillatory behavior, but it's damped. So it dies out. However, there's something in the system that is controlled by a parameter. So I've got this little mu parameter. And here at this value, things are nice and stable and they decay. As I turn that knob up, I don't know why I feel like I have to draw my little knobs, to some critical mu value, we start to see resonance and a building up of energy. And in a physical system that was designed to do this, that's pretty fucked up. That's a bad thing. One of the things I want to come to you with next Monday is like some actual physical examples of this stuff. I don't have any today. We're going to read some in the book, but I want us to understand it a little bit more. So here's the archetype of a Hopf bifurcation. We have R dot, and we got to do this in polar form because the oscillatory stuff is best studied in polar coordinates. Minus R cubed. We've got theta dot equals omega plus BR squared. 3 parameters. That's a lot. That's a lot. That's one more than the most we've seen.
Oh, jeez. We're pushing it here, Dr.
Yeah, crazy. So notice how this is a minus R cubed.
Mhm.
So that means this is a stabilizing term. So this works to stabilize because it's always acting opposite of R, right? R is going to a number between 0 and 1, and this diminishes R, so this is a stability term bringing us back in. This mu parameter, though, controls ultimate stability at the origin. So this mu controls stability in a couple of ways. We'll see how it works, but for large magnitude R, this is the dominant term, but when R is in the range near the origin that we're interested in, mu is going to control the stability. This controls the frequency. So this is your kind of your main frequency control. It's a constant, and it's just telling you how fast, it's telling you what d theta dt is. It's just telling you how fast to click around. This tells you how much the oscillation depends on the magnitude. So as B gets larger in value, the rate of spinning depends on the magnitude even more and more, and becomes very complicated. So this B here controls dependence, controls frequency dependence on magnitude. Of R. Let's go like that. So even though there's 3 parameters there, we can actually get, I don't know where my eraser is. I like how I just have to look sad and you help me. It's nice.
There, Dr. T. It's okay.
There. Do you watch Sanford and Son at all? You two, do you know who I'm talking about?
No, sir.
Okay, moving on again. Okay, so let's forget about this, because this is just going to be like spinning at different rates. But this is going to be the stability stuff. So we've seen this before too. We've completely seen this before. Let's take a look at it, like what that might be. So here's R dot, and then here's R. And let's say mu is a positive number. So when mu is a positive number, let's say like mu equals 1. I like to just get things to be nice and easy to work with for intuition. We've got that. And so that's R times 1 minus R squared. So that's R times 1 minus R times 1 plus R. We are still assuming that R is always a positive number, so this R equals -1 isn't going to really do a whole lot for us. But we can imagine this thing is just a cubic that looks like this. And then we can say, we don't need negative R. So we just want R greater than 0. This is a 1 right here. And then now I can generalize, right? If this was just mu here, if there was a mu in front, then this would be a mu here, and then this would be square root of mu, and this would be square root of mu as well. And this point would actually be just good old square root of mu. Is this a stable equilibrium or an unstable equilibrium? So here we see that R dot is 0 right there, no change.
Unstable.
Yeah. Wait, no, stable. Because here R dot is positive.
Yeah.
And like so. So here we have stable node. And this is a circle of radius square root of mu, and it's stable. So that means if you're on the inside and mu looks like, we'll assume omega is positive. If you're spinning clockwise, counterclockwise, we're going to have this kind of behavior. So we see that there's a limit cycle right there. And then on the outside of that, R decays. So we see cycling in like that. Stable limit cycle. Nice. that occurs when r becomes positive. When r is negative, what do we have? Well, when r is less than, when omega is less than 0, well, let's do the boundary case first. When omega equals 0, we've got r dot equals negative r cubed. That's pure decay. That's just spinning in toward the center. So this is a stable spiral. And then when r is less than 0, it is also a stable spiral because mu will always be a negative quantity at that point. So we'll just kind of put that there as well. And this should say mu is less than 0, not r is less than 0. So what happens is, if we're looking at the bifurcation diagram, and here's your parameter mu, up until here, we've just got a stable spiral. So stable spiral. And then the minute we hit over here, what we start to see is this limit cycle that's born. And this is going to be an abuse of, this is such a terrible abuse of bifurcation diagram, but I kind of hope it makes sense. In here, we're going to see these oscillations start to grow inside there. Does that make sense? Because as mu gets bigger, then that circle, that limit cycle just starts to grow. And so you see something that was once a beautiful, stable thing now becoming this thing with crazy oscillations that grow as mu grows. So in here, oscillations form, unstable oscillations form and grow with mu. So that's kind of the classic Hopf bifurcation. Something that was once stable but spinning starts to get this unstable center that starts to grow out toward the side. Kind of cool, yeah, not bad. This is a supercritical Hopf. This isn't the worst kind. That seems pretty bad. That seems really bad. But in like an engineering case, this parameter mu, like once you see this thing is growing, you could maybe control mu and keep that oscillation from getting too big, right? Maybe you have some vibrations. Maybe you can control it so that this thing never gets above a certain level. And maybe that would be good for you. So you could potentially control that thing. It's still at least moving around the center. It's the subcritical Hopf where things become terrifying.
Oh, good.
But before we get there, which is exciting, right? There's this like terror around the corner. Do you like horror movies? Do you like horror movies? You're not a horror fan. I love horror stuff. I like being scared.
I'm scared.
I wish I was that scared, because then I could get scared.
Dude, you just don't get that vibe from Trinity.
No.
No.
That you're a scaredy cat?
You don't get that vibe out of a scaredy cat.
No.
Yeah, not at all. It must be really, you must be kind of like, it must be intense playing Last of Us. Because it's pretty immersive. Yeah.
She gets
I'm
through it.
trying to, I've always been bad at those types of games. So I'm trying to just like, be like, it doesn't matter if I die. You literally just start over
It's
from
true.
the encounter, like it's fine.
0 penalties.
So
Yeah.
I'm working through it, but when I first start games like that, and I need to like get used to it, I'm petrified. It took me like 20 minutes to get through my first encounter when there was only like 3 clickers around and I could just see
You were just
past it.
waiting for the right moment. You were hiding and just.
I
like,
made sure I
yeah,
could
yeah.
map every single one of their like loops so I knew exactly where they'd move because I was like, I'm not.
That's
Sick.
awesome.
I watched the animation of Joel dying at least 4 times and I said, I'm not doing
No,
this again.
no.
I'm not doing this again.
No.
No,
Wait, you've gotten to that point?
No, I mean I'm not talking. I'm
Okay.
talking about like when you're just like in an encounter and you die.
Oh God. Oh, okay.
No, but I already know that.
Okay, and I was like, shit, and I shouldn't have said that, but
No, I already know. It's fine.
it's horrible.
No, I know.
I don't ever want to see it in the show.
I don't either.
I hated it in the game.
I never want to see it.
It's just,
But it's gonna have to happen.
it is gonna happen.
Devastating. But no, when you're just like in an encounter and you die, like I can't watch this again. I can't watch this again.
And then in part 2, Abby comes in. She's badass. The model, I don't know if you know the story. So like they used this, an actual human
Yeah.
person to model Abby. And she was so fucking ripped that all these all these bros, these
Yeah.
douchebag gamer bros,
Yeah.
were like saying, oh, that's not modeled off a real woman. No real woman could look like that. And then she's like,
Hello?
just
She said, excuse you.
she's a horrible Karen.
Oh.
But sympathetic in a way.
Okay.
But man,
You're right.
No, don't say fuck Abby. I mean, yes and no.
Yeah. Yeah.
Yeah. I love women, so I can't really
Same.
like, be like.
Yeah. What am I doing? Oh,
I don't know, I'm sorry.
I want to do a stability analysis on this.
Oh, sure.
Could you? We have like 10 minutes, 12 minutes left. Friends, could you convert that to rectangular form for me, please? We never do that.
Wait. That's...
So let me help. Let me
I
help.
have a hangnail.
Here's what you're gonna want to use. So these were the equations. We're gonna do this backwards. So you're gonna use x equals r cos theta.
Yes.
Y equals r sine theta. Are you muttering things at me?
No.
Because I'm pretty sure I detect muttering.
No, sir.
Okay. So x dot equals r dot cos theta minus r sine theta theta dot. Just do that one. So convert. So convert, please convert this and just find the x dot equation using the methods we've already seen. It's not going to be too bad. I
Somebody
did
get
this.
this hangnail off of me. Ah!
If it'll stop the muttering, I'm all for
I'm
it.
sorry.
Muttering small talk at the walls. That's from a Bob Dylan song. He's like talking about somebody. He's like talking shit to him.
I don't mean to.
Ooh, and I can go do
Go pee.
my thing that I
Yep.
do, you know, as a lot of humans do it.
Fucking love that guy. I fucking love that guy.
So.
You're such a fucking character, dude.
Yeah. I'm not simplifying that.
Is there not supposed to be a dot above the r with r sine theta?
Correct.
Okay, that's purposeful then.
Yes.
Okay.
Just a regular R.
Wee little aw.
Yeah, hopefully you didn't want any spoilers from The Last of Us, because he just kept talking.
I have no idea what you guys are talking about usually ever, so like
Okay.
it's fine.
Okay, cool.
Really, it's okay.
Okay, because I feel bad.
Really, just continue distracting him and
I literally just have to get him talking about The Last of Us. We're golden.
honestly, it's The Last of Us with Dr. T and anything sports related for Cyber. Hello, recording. Yes.
He made me put The Last of Us in my thesis. And like it makes sense to put it in there.
Was
But he was like, you know, The Last of Us is a really good example of what you're trying to talk about. Okay.
You said, alright.
Okay, I'll put it in there.
Yeah, you got it. I don't want to simplify this.
I literally don't. That's ugly. Is there even a way to simplify it?
Not nicely. Maybe. I just substituted and they gave up. Okay.
Okay, I'm just gonna assume what y dot is.
I'm just.
It's
Okay.
my best educated guess. Actually, it's probably in the book somewhere. Oh my god, it's in the book.
R sine theta is y.
What the
I hate it when that happens.
Shit. Okay. Oh wait. Okay, I know what we need to do.
Yeah.
I know what we need to do.
That makes more sense. Am I missing an R? Where'd my other R go? I am. God damn it.
Oh wait, where'd my arrows go? I'm cheating and looking at it in the book.
Oh shit, I have a beta value equation. What am I doing? Silly goose.
It's not looking good.
That's inconclusive.
Yeah. I'm sure it will by the end of it.
I'm just going through the fun
Oh
stuff.
my god, I'm so
Yeah, that's a
stupid.
fine. Oh, God, I actually got myself.
I'm so stupid.
You are not stupid.
Well,
Wait, is that,
I'm glad one of us.
is that an R squared equation?
Is that what? A depth?
Oh, it is an R squared. Okay.
Yeah.
Okay. What am I looking at here? I'm just gonna.
I have stuff and things.
So
I'm gonna get rid of this freaking cosine.
Yeah, you can. I just scribbled that. That was my epiphany moment.
What did you do exactly? Did you happen to multiply this by R, did you? I'm wondering if that could do that.
I didn't.
I did not do that.
I
You
did.
can do that.
I
It
mean,
just
go
seems like
crazy.
it might open up a few, you know what I mean?
Yeah.
A few things.
Okay, because then you have.
Right, because then you get that nice R squared.
I mean, I ended up getting an R squared out of there. It just took me a while. I mean,
Oh, did you? Okay, yeah. There's definitely many ways, and then we replaced this with that.
Okay. Yeah, I did that. I did that first.
Oh, you did that. Okay, that seems reasonable. It seems quite reasonable. This seems like I'm going down a hellhole.
Uh-huh.
Yeah.
That's what we said.
Yeah. Wait a minute. This doesn't seem right.
In the damn cell.
This doesn't seem right.
Okay,
You just went straight in, and so let's take a
So-
look. Yeah.
the first line, yeah, if you start with the first line, I did,
You plugged the R dot
I
equation.
plugged R dot in, yeah. And then,
Theta dot.
yeah,
Here. Okay, that all sounds completely reasonable. Be R squared.
yes.
It's an omega. Okay, cool. Did anything great happen? Doesn't look like.
Well, doesn't R sine theta turn into Y?
Yes.
Yes.
So, yeah, I put a Y there,
You can pull an R out of the
yeah,
first part, and then you have an X. with
Yes.
R.
So here, oh, right, yeah, beautiful. So we get X times, and then we're left with mu minus R squared minus Y omega. Okay, yeah. We're getting there. Oh, this is nice. This is great. Then R squared is just X squared plus Y squared. Beautiful. So X, mu X. Let's pull the linear terms out in front. So mu X minus omega Y minus X squared plus Y squared minus YB X squared plus Y squared. Yeah. So this stuff's all order X cubed, Y cubed stuff here. So those are all higher order things, right?
Yeah.
Yes. So near zero, where we're interested in doing our classification, these aren't going to play a role, these higher order terms. In other words, if we linearize near zero, these are the terms this is the system we have. So in other words, I mean, think about what the Jacobian's going to look like, right? So if I do the Jacobian in terms of X and Y, it's going to look like mu, 0, and then higher order stuff, but it's all going to involve X's and Y's. so that when I plug in 0, 0 here, it will dissipate. So J at 0, 0 is just gonna be mu negative omega. And then we didn't do the y dot equation, but I can tell you what that's gonna look like. The y dot equation equals omega x plus mu y plus cubic stuff. And so the Jacobian there is going to be omega mu. Groovy, groovy, groovy.
Ruby.
Groovy. Then, now we're in a good spot. Now that's the Jacobian of the center of this crazy system here.
Okay.
So we understand now, we can get at the eigenvalues and the eigenvectors. So the eigenvalues of this are already pre-computed. And they are lambda equals mu plus or minus I omega.
Oh. Okay.
So they're complex. Right, and just here, just to make sure that we all know what I'm talking about. So you would get the roots of mu minus the trace. So that's 2 mu. Lambda plus the determinant. What's our determinant? Omega squared plus mu squared. So those are the roots of that guy.
I really just think omega should be an O instead of a W, but
Take it on the Greeks.
damn Greek letters.
Take it up
Omega.
the Greeks.
What's that about Greeks?
I'm gonna
Just take it up the Greeks.
take it up the Greeks.
Yeah. It shall henceforth be called Womega.
Woman.
Just for you.
Yes.
Woman, like woman, Womega.
Yes.
All right, there we go. Take it back, own it. Well, let's look in the complex plane. So, here's the complex plane, C. Here's where these eigenvalues are. You've got them as a conjugate pair. So this is omega, mu, omega, and then mu minus omega. They're like this. So now remember what happened over here. When omega was negative, let's actually draw that here. So let's here's omega, here's negative omega. When omega was negative, or mu was negative, we were over here. So with these two, the pair, when mu is less than 0, is over on this side. Those are stable spirals. So we've got the real part is negative, and the imaginary part is imaginary and non-zero. But notice, remember how this went. As mu was negative, we had this stable spiral. When mu was 0, we had a stable spiral. It was the minute mu became positive that things went bad and we formed that cycle. That means these eigenvalues, or that corresponds to these eigenvalues moving across the imaginary axis. So here, the real part is positive. And here, the real part is, the real part is negative over here. Real part is positive over here. So you move from stable spirals to unstable spirals. Key thing of all this is a Hopf bifurcation occurs, corresponds to eigenvalues moving across the imaginary axis, corresponds to a pair of complex evals moving across the imaginary axis. And that's going to be one of your diagnostic tools for your homework. Imagine. You think now you're doing South Park?
SpongeBob.
Oh.
Imagination.
Is that where that's from?
Yeah.
Huh.
Are you doubting me, Dr. T?
I am not doubting.
I know
I know
SpongeBob.
no SpongeBob lore. I know a lot of South Park lore, and you're
Oh, I
right.
got you with SpongeBob. I love SpongeBob.
a South Park fan?
It was like that subsection of comedy shows I wasn't allowed to watch
Oh,
when I was a kid.
Oh, interesting.
So
Yeah, you never got into it.
Family Guy, South Park,
I don't
Bob's
like Family
Burgers, those types of shows though, those animated shows, I was never allowed to watch.
When my brothers got old enough to watch them, then my mom and dad were really like,
I was really allowed to watch SpongeBob. My dad thought it was so stupid.
is it
It was too stupid to watch? It wasn't that it was
He
like.
thought it he genuinely thought it killed brain cells.
Okay, sometimes, have you listened to Patrick Star talk?